Today's lesson, we're going to start by learning about curve sketching, where we put everything we've learned together. So without further ado, here we go. Number 1, supply the requested information, and then we'll check our answers by graphing. All right, the first thing I ask for is 2 derivatives, so we'll take the first derivative, and the second derivative, which will be 36x squared minus 48x minus 96. All right, in order to answer the other questions, we're going to have to do some factoring. Let's start with the first derivative. For starters, we can take out a 12x. That's going to leave us inside with x squared minus 2x minus 8. And since we're looking for critical numbers and where it's rising and falling, I'm going to set this first derivative equal to 0. It can factor once more. 12x is still out front. But now we get a pair of binomials in the form of x plus 2, x minus 4. Which gives us our critical numbers of 0, negative 2, and positive 4. All right, as far as finding the rising and falling, I'm going to make a quick sign chart. Again, we have to put these in order, so negative 2 must come before 0. Don't get sloppy accidentally. And I think the easiest place to test it would be right here, the fully factored first derivative. So we're going to try a number less than negative 2. How about negative 3? Why not? If you put a negative 3 in for all the x's, I think you can see you're going to get negative times negative times negative, which is, you guessed it, negative. So the graph is falling, the original graph I should say. Let's try something between negative 2 and 0. How about negative 1? Inserting the negative 1 for the x's will be negative times positive in the middle times negative. That's a pair of negatives that cancel. That makes an overall first derivative of a positive, I should say. And that's going to make the slope positive as well. So the graph of f of x will rise. If we repeat this with, say, positive 1, you're going to have positive, positive, negative. So that's going to fall. And finally, if we say plus 11, which is greater than 4, all 3 are positive. The first derivative in turn is positive. The original graph will rise. So our regions have been figured. We just have to write them properly. So we'll start out with the rising. And we need hard brackets here. Remember, you're going from negative 2 to 0, inclusive, union with 4 to infinity. Of course, you can't reach infinity, so that's curly. And then the falling, similarly, will be negative infinity to negative 2, hard bracket that negative 2, union with, and it's also falling from 0 to 4. Both in hard brackets, because that's what you do with rising and falling. Okay, that's it for the first derivative. Now we move on to the second derivative. We're going to factor it as well if we can. The only thing we'll be able to do is take a 12 out, but that's something, so let's try that. I'll set that equal to 0. Obviously 12 can't be 0, so it's going to be the items inside the parentheses that have to do the dirty work. And that is not factorable, not at all. So we need to use the quadratic formula. If you try the quadratic formula, you're going to end up with 2 plus or minus 2 rad 7 all over 3. I think I'll go decimals instead on that. That'll be our 2x coordinates of our points of inflection. Negative 1.097 and 2.43, either 0 or 431. It's 2.4305, so you can either round it off or truncate it. Let me write those down. All right, let's make sure those are, in fact, points of inflection. So I'm going to make a quick, again, a little sign chart. Do the negative 1.097. Here we're going to call this 2.43. I'm going to call it 2.431. Really, it's 05. You can either leave it as 430 or 431. All right, let's see what's happening here. If you try something less than negative 1.097 and you plug it into the second derivative, you're going to see that that will, in fact, be concave up. It's going to end up being a positive number. I'll let you try that at home if you'd like. If you try something in between them, I think it's pretty easy to see if you plug 0 in, you're going to have 12 times negative 8 inside the parentheses. That's negative. That's going to be concave down. And if you try a really large number, the 3x squared will dominate. That's going to turn the parentheses positive. Again, I encourage you to check that. I'm just, for the sake of speed, going to let you know that that is what happens. And so we are concave up on the edges. So from negative infinity to negative 1.097. I realize that is rounded. We're going to forgive ourselves. We always curl it, though. Union with 2.431, 2.4305 if you prefer, to infinity. And it's concave down in between them. All right, so far so good. Let's take a look at another page. Some additional information that we need. X and Y intercepts. The y-intercept will be easier, and I'm not sure why I made it plural, because you can only have one y-intercept, otherwise you're violating the vertical line test. It's simply going to be 0, 5, because the y-intercepts happen when the x's are zeros, and you can see that that gives us a whole bunch of zeros plus 5. The x-intercept, you'd have to set that entire equation equal to 0, so you'd have 0 equals 3x to the 4th minus 8x cubed minus 48x squared plus 5. If you do that, you're going to actually get 4 answers. All 4 answers are intercepts. The only way to really get that is to graph it. And so I'm going to do that right now. Okay, I have graphed the original equation. Our problem does say check your answers by using graphing technology. It looks like we're going to kind of do that a little ahead of schedule, which is fine. Let me hit zoom standard. And you can see that we do cross the x-axis 4 times. Let's find them. Second calc, 0. Left bound. I don't know if you realize you can actually type a number in. You don't have to sit and tap the arrow and make it go forever. You can just simply type in, negative 5 and say negative 2. Might save you a little time. You want to guess? Yeah, sure. All right, so one of the answers is negative 2.859. You can also say negative 2.858. Again, that really is y equals 0. Sometimes the calculator will give you those funky values that are, like 1 times 10 to the negative 11th. That's a glitch. That really is 0. If you repeat this process 3 more times, you'll get the following answers. And by the way, that third answer, that 0.316, that can also be 0.315 because it's 5.5. So I rounded it up, but you could also truncate it. Either way is fine. Vertical asymptotes. We're not going to have any. And the reason why is we're not dividing by 0 because we don't even have a fraction bar, so no worries there. There are none. The horizontal asymptotes, we're not going to have any of those either. This graph is simply looking like a W, therefore no asymptotes. And the reason that there are no horizontal asymptotes is because of what we call end behavior. And that is the limit as x is approaching infinity. And also the limit as x approaches negative infinity. I'll put that over here. And in both cases, it's going to be infinity. This 3x to the 4th is the dominant term. And even if you plug a negative infinity into it, you're going to have 4 negatives being multiplied together. That will be positive. And that's going to overpower all the other terms, and it's going to cause the graph to go up in both directions. And you can see that when you look at the graph. You can see that as you head out to the right or to the left, it's heading up to the sky. That is a big W if I were to zoom out a bit. In fact, I think I will. You can see that the maxes and mins are behaving exactly as we said they would. There's a min right here at negative 2, a max at 0, and another min right here, and that's going to be at positive 4. Negative 2, 0, and positive 4 were our critical numbers, you may remember from the first slide. And we predicted that there'd be a min at negative 2, there'd be another min at 4, and a max at 0. So that checks out nicely. All right, moving ahead to number 2. Here we have a fraction. This could be a little more involved. Before I take the derivatives, let me go ahead and go to the second page. I think it'll be easier to start there with any fractional problem. I'm going to go ahead and factor because factoring is generally just a good idea. The x squared minus 9 in the denominator factors beautifully as the difference of two squares. Up top, you could take out a 2 from the numerator, leaving you with x squared minus 2. All right, so we do have some vertical asymptotes this time. We have an x plus 3 and an x minus 3. They're not going to cancel, and that's going to be a big deal. So x being negative 3 or x being positive 3 will form those two asymptotes. A horizontal asymptote will also occur, but more on that later. Let's grab some x and y intercepts. The y-intercept, I think, is easy to see. If you make x 0, you'd be left with positive 4/9, because the negatives will cancel out. And the x-intercepts, you'd have to set y equal to 0, which really means you're just setting the numerator equal to 0. The denominator won't matter. And so x will be plus or minus square root of 2. And the square root of 2 is 1.414, just to give you an idea once we see the graph. All right, I'm going to come back to the horizontal or slant asymptotes and the end behavior later. Let's head back to that first page. For the derivatives, however, I am not going to factor because it's already a quotient rule, and I just don't want to make it any worse than it is. In fact, whenever you have a problem like this that's rational or fractional, and the degree, or highest power, of the numerator is greater than or equal to the degree of the denominator. In this case, we've got a pair of x squareds, but if it's top-heavy or it's tied, you want to long divide. Believe it or not, you want to do this. So I'm going to do some long division with letters over here on the right. All right, let's see what we can come up with. Let's start with just the x squared and the 2x squared. That's normally what we do. When you guys were little kids and you were doing like an incredibly long division problem, they usually didn't say to you, hey, how many times does 6 go into 231,479? They'd only have you look at the first part and maybe ask you, hey, how many times does 6 go into 23? I'm doing the same thing by only looking at the first term. That's just kind of what we do. And you say to yourself, hey self, x squared times what is 2x squared? And hopefully you answer back, 2. And sure enough, that's exactly what it is. You put it up top. We're trained to multiply when we were young. We're still multiplying. It's just bigger, stronger, faster. It's the distributive property that younger kids don't know about. And then, this is the step that most students, if they're going to make a mistake, will make it here. You draw the line and you change the signs. Why did I do that? Because your 3rd or 4th grade, 5th grade teacher, whatever it was when you first learned to long divide, said, all right, we're going to subtract now. And they put a minus on there. They changed the sign and nobody questioned it. I did the same thing, but being a binomial, maybe a trinomial in cases, I've got to change all the signs. All right, this should drop out. If it doesn't, we put the wrong thing up top. And when we combine this, we didn't need the 0x, I just had it there for safety's sake. We get positive 14, which is our remainder. So the original problem, instead of being f of x is 2x squared minus 4 over x squared minus 9, the original problem was actually equal to 2 plus fraction. 14 over x squared minus 9. Just build a wall right here. What happens if x gets really large or really small? Let's say x is 1,000,000. You've got 1,000,000 right here, and you square it and take away 9. That's going to be so large that 14 divided by it is pretty much going to be negligible. It's going to be 0. And same thing, if x is negative 1,000,000 or negative 1,000,000,000 and you square it, it's going to overpower the 14 up top. So you're going to end up with 2 plus 0. So as you head towards the ends, I'm going to go back to page 2 here, you will be getting closer and closer and closer to 2 plus 0, which is 2. And that will simply be our end behavior. As x approaches infinity, the function's heading towards 2. And the same thing if you're plugging in really large negative values, which I guess would be small, technically. You're heading towards 2. You'll never get to 2 because it's never truly 2 plus 0. It's 2 plus, small, but you still have the 14 up top. And since you never get to 2, but you get closer to 2 and you start approaching it, that's going to be our horizontal asymptote in both directions, y equals 2. On this particular problem, there was no slant asymptote, just a horizontal. You can't have both a horizontal and a slant at the same time. If it was possible, let's say this is a horizontal asymptote here. Let's say you have a slant asymptote here. If you approached both of those, your graph would look like this and it would violate the vertical line test. So it's going to be one or the other. All right, we got the back page done. Let's head back to the front page on number 2. We need to get some derivatives taken. And now that we've done our long division with letters, it'd be a lot easier to take a derivative of the new thing. Let me make some room for myself. All right, first derivative is going to be negative 14 times the quantity x squared minus 9 down by a power, so to the negative second. Oh, but there's a chain rule of 2x. So that's going to end up making negative 28x times quantity x squared minus 9 to the negative second. Okay, so that is the first derivative. Put a box around that. The second derivative, unfortunately, we're going to have to take that first derivative and do a product rule to it. Oh boy. So the u will be the negative 28x. The v will be the rest of it, the parentheses, to the power. So hang on tight. Here we go. We're going to have u prime v, so that's going to be negative 28 times x squared minus 9 to the negative second plus uv prime, so plus u, which is negative 28x. And v prime is going to be negative 2 times x squared minus 9 to the negative third times another chain rule, additional 2x. Egad. All right, to simplify that, I'm going to go ahead and take out a negative 28 because both terms have it. Let's see if I can fit this over here. I'm going to come over to the right. I'm going to switch colors as well. I will go with some blue. We'll take out a negative 28. All right, we're also going to take out an x squared minus 9 to the negative third power. Let's see what that leaves us with inside some brackets. Here, I've taken out everything except we're going to have an x squared minus 9 remaining. I can put parentheses around it if I want to. It's not necessary. I think I will. Over here, we've taken out the negative 28. Taken this out. But we still have a negative 2x times a positive 2x. That'll be negative 4x squared. Okay, to clean this up a little bit to get our final second derivative, you can see if I combine like terms, that's going to be negative 3x squared minus 9. I can take a negative 3 out of that. I'll multiply it by the negative 28 in front. Negative times negative, it's positive. 28 times 3, that'll be 84. This is crazy. X squared minus 9 to the negative third is still there. And then finally, remember I took the negative 3 out of that, so that'll just be x squared plus 3. And that, my friends, is the second derivative. I'll put a cloud around it. Wow. Okay, let's look at some rising, falling, etc. Back to the first derivative for that. For the first derivative and for rising, falling, you need your critical numbers. So you take the first derivative, set it equal to 0 right here. Obviously, x equals 0 is going to be one candidate. And the others will come from the first derivative being non-existent. Remember, critical numbers either make the derivative 0 or does not exist. So 3 and negative 3 are also considered to be critical numbers, even though they're not in the problem domain. Now, if I asked for critical points, you wouldn't be able to use 3 and negative 3 because they're not points on the graph, but they can still be considered critical numbers. And so they're still part of the sign chart that I'm making right now. Negative 3, 0, positive 3. Again, remember to keep them in order. That's important. And you're going to try a number from each region into the first derivative. The first derivative, if I bring this down, I know I'm getting a little sloppy here, but I'll try my best to not go too crazy. I think everybody can agree that, oops, I need an X here. The denominator is never going to be negative because it's squared. It could be 0 if you try the 3 and the negative 3 in, but we're not allowed to try them in. Those are border points. We have to pick something else. So down here, this is going to stay positive all the time. A positive number down here. So really, it just matters what you put up top. And if you put a negative number in, you're going to get negative times negative, which is positive. So the graph will be rising if you're to the left of 0. And if you try a positive number in, like a 1, 2, 4, 5, you're going to have negative times positive. That's going to be negative, so the graph will fall. All right. Now remember, we have vertical asymptotes at negative 3 and positive 3. So my guess is that this will probably connect like so. And this will be some sort of an asymptote-looking thing. That's a fairly good prediction. Let's get the rising and falling written. We're going to rise from negative infinity to negative 3. Normally, you would put hard brackets on this, but at negative 3, you're not rising because you don't exist. There's an asymptote, so you have to curl it. Union with positive 3. Sorry. Let's try that again. Union with, again, curly on the negative 3 to 0, but we make it to 0, so we have to hard bracket that. Okay, so you're rising here and here. You're falling the rest of the way, so you're falling from 0 to positive 3, which again cannot be included because it's an asymptote. So you're falling here, and then you fall some more, so union positive 3 to infinity. Again, notice that I'm not doing a hard bracket on the 3 because we're not there. All right, first derivative has done its job. Time for the second derivative. I need to clear a little bit of space. Let me take the second derivative, bring it over in the middle, and write it a little more neatly. We have 84, a positive number. We have x squared plus 3, a positive number. No matter what you put in for x, you're going to square it and then add 3. You're going to have to be positive. So the numerator here is positive all the time. The denominator is not. It's x squared minus 9. But down here it's to the third power, which is not even. So we are going to have some change-ups. The only places that could possibly be points of inflection would be 3 and negative 3 because they could change the signs of the denominator. I'm going to put them in, but this is unofficial for now. I may have to erase this. I may be able to keep it. Only a sign chart will tell us for sure. as I mentioned moments ago, this numerator up here is positive no matter what. So let's just try the denominator. If I try something in the middle, between 3 and negative 3, let's say I try a 0. I think you can see 0 minus 9, you're going to get negative 9 cubed. Negative times negative is, of course, negative, so concave down. If you try something larger than 3, say like you try an 8, 8 squared, that's 64 minus 9. That's definitely positive enough, and it's getting cubed nonetheless. If you try a negative 8, you're going to end up with a negative 64 minus 9. Again, that's a positive number, and you're cubing it. So in those regions, you're going to be concave up. So yes, 3 and negative 3 were both points of inflection. And we can write the rest of our answers over here in green. It's concave down in the middle. Remember, concavity is always curly. And it's concave up out by the extremes. So from negative infinity to negative 3, union with 3 to infinity. And that's it for our second problem. Last but not least, number 3. Let's start by taking some derivatives. Oh boy. We've got ourselves a quotient rule here. That's okay. I'm not afraid of it. Not too afraid, at least. U prime v minus uv prime over v squared. I'll leave a lot of room. V squared's not going to be bad. That's just simply going to free up the x squared plus 1 from its square root. All right. U prime v. That's going to be the 3. That's the u prime. And the v is x squared plus 1 to the 1/2. It's not negative a half. I realize it's on the bottom, but that's where v lives. Okay, u prime v plus minus, this is quotient rule, minus u v prime. And v prime is going to be 1/2 x squared plus 1 down by a power, so now this is negative a half, times a chain rule of 2x. All right, this is a little bit ugly. I was sort of afraid of that. We can lightly cancel the 1/2 and the 2, so that helps. And we can factor a little bit, so I'm going to continue to simplify this. I can factor out a 3, and I can also factor out an x squared plus 1 to the negative half power. Okay, when I do that, I'm going to simply be left with x squared plus 1 right here. And I can put a parentheses around that. I don't have to. Why not? This minus sign comes down. The 3 is already gone. So is the x squared plus 1 to the negative half. So this is already gone. This is already gone. All we're left with is x times x, which will be x squared. It's kind of weird that I wrote that in green, but not to worry. It's going to cancel out anyway with the other x squared that's positive, leaving us with just a 1 in the parentheses, which means we don't need the parentheses or the bracket at all. And then this x squared plus 1 to the negative half can come down, and we can have 3 over x squared plus 1 to the 1.5, or heck, we can bring it up top. Let's do that. 3 quantity x squared plus 1 to the negative 3/2. Remember, 1 is 2/2. If you bring it up, it can join forces. That's going to make the second derivative a lot easier because now we don't have to fumble around with a quotient rule anymore. So that's great. Okay, second derivative, we'll take that in, let's go with some purple right below it. So the second derivative is going to be negative 9/2 stuff, which is the x squared plus 1 parentheses, to the down by a power, so that's going to be negative 5/2, negative 2.5, times a chain rule of 2x. Again, the 2 will cancel with this 2 down there, so that's going to end up making a second derivative of negative 9x times quantity x squared plus 1 to the negative 5 halves. Whew. All right, those are our derivatives. All right, let's look at critical numbers first. That'll be from the first derivative. And there's no way to make x squared plus 1 0 or negative. And so we don't have to worry about the first derivative ever changing signs because, quite frankly, it can't. So critical numbers, there are none. And since there are no critical numbers, that means it's not going to change direction. So rising, falling, it's either all or nothing. Let's rewrite this first derivative as 3 over x squared plus 1 to the positive 3 halves. I think it's easier to see right here in the rewritten first derivative that the numerator is positive all the time because it's a 3. The denominator is positive all the time as well. If the first derivative is positive all the time, the graph will rise always. I could also write negative infinity comma positive infinity, and it will fall like never. So that is great. Okay, let's play around with the second derivative. I'll go back to that nice attractive purple color. So let me take this guy, bring it down here, and we're going to call it negative 9x over x squared plus 1 to the 5 halves. Now again, x squared plus 1 is positive all the time. Taking that to the 5 halves will always be positive. So it really just depends on this as to whether it's going to be concave up or concave down. And that means that the point of inflection, if there was one, would be x equals 0, or else there aren't any at all. I will write x equals 0 for now. And if it turns out that it's not a point of inflection, I'll scribble it out and I'll write none. Let's see if x equals 0 is, in fact, something that's going to change the sign of the second derivative. It will. You can see if you plug a negative number in, you're going to get negative times negative, which is positive. Second derivative positive means we're concave up. And if you try a number into this x that's greater than 0, you're going to get negative 9 times something positive. That's going to be, negative times positive is negative. That's concave down. And concavity, concave. It's always curly parentheses, not hard brackets. So x equals 0 was a point of inflection. We'll try the rest. The x-intercept and the y-intercept will be the same thing here. And it's going to be the origin in both cases. 0, 0. Because if you make x 0, I think you can see that that's 0 over 1. If you set this equal to 0, x would have to be 0, because how else are you going to make the numerator 0? So this thing is going to go through the origin. It will not touch the x or y axis any other place except for the origin. Vertical asymptotes. I've already said several times that the square root of x squared plus 1 cannot be 0. And if this can't be 0, we don't have to worry about dividing by 0. So therefore, there are no vertical asymptotes. All right, horizontal asymptotes, end behavior. These are synonymous. Let's start with end behavior first, even though I'm a little bit out of order. Let's take the limit as x approaches infinity. We'll do that first. What if x got really large? Well, if x got really large, this plus 1 at the end isn't going to matter. Can you imagine x being a billion? A billion squared plus a dollar bill. If you're a billionaire squared, you're not going to care if somebody tries to bribe you with a George Washington, a $1 bill. So really, that kind of doesn't matter much anymore. And then you have 3x over the square root of x squared. That's just x. And that's going to end up being 3, which is exactly where this is going to head. So that's the end behavior to the right. Now, it seems like it would be the same to the left as well, but it won't be. As x approaches negative infinity, the same sort of thing happens. That plus 1 isn't going to matter. I scribbled it out. It's still gone. Square root of x squared is still this x, and the 3x is still itself. But this time the x's don't cancel. And the reason why is this. X is very negative, which means that this 3x up top is very negative. This x was very negative until it became x squared and it changed positive. So yeah, the x's cancel as far as the decimals or the numbers that they are, but you had a negative divided by a positive, that's going to be negative 3. And so the other limit is negative 3. And so therefore, we have a pair of horizontal asymptotes, y equals 3 and y equals negative 3 both serve as horizontal asymptotes. We're going to take a look at this. It does say check by using graphing technology, so let's go there right now. Okay, I typed it in. Let's see what it looks like. Let's go zoom standard, because again, I was zoomed way out before. That's exactly what we predicted. There's a point of inflection at 0, 0. It also is the x-intercept and the y-intercept. And you can see that there are no vertical asymptotes, but there are horizontal asymptotes at y equals 3 and y equals negative 3. If you're not sure if it's going to ever go above 3, you can always sneak a peek at the table. As we move up the table, table's kind of going backwards, that's weird. You will never cross 3. You're going to get closer and closer and closer, but you're never going to pass it. Even if you typed in 9999, it won't. You're safe. All right. Fantastic. That's exactly what we predicted. Remember we said that the graph was always rising, never falling. That shows up here as well once we saw the graph. It's rising all the time. It's even rising out at the edges. Even though it's not going to ever go past 3 here, it's still very slowly rising. What we found was true. All right, that's it for the section on curve sketching. Good job. We'll see you next time.